In the last video, we talked about how defects in TMDs could lead to interesting physics, such as photoconduction. In this video, we're going to be talking about how imperfections, such as deficiencies of certain types of atoms, can impact charge transport. We will also be looking at other interesting properties of this semiconductor, such as its insulator-to-metal transition, and how conduction appears in the edge before the rest of the bulk. First, I would like to talk about semiconductor devices, specifically the field effect transistor, or FET. To put simply, FETs are devices that use an electric field to control the amount of current passing through a semiconductor. FETs have three terminals, a gate, a source, and a drain. By applying a voltage to the gate, we can change the conductivity between the source and the drain. One of the reasons we are using TMDs in combination with FETs is because the measurements involving them are inherently in the mesoscopic realm. What we're specifically interested in is how the electrical inhomogeneities in TMDs lead to interesting hopping and percolation properties, which are fancy words describing how electrons are transported and interact with their environment through the device. Spatial conductance maps would be highly desirable because they help us understand how the broken symmetry on the edge and how electrical inhomogeneity contribute to overall charge transport. In this video, we're specifically going to be looking at MOS2 FETs. The experimental setup is shown here. MIM is used once again to scan over a region. The reflected signals are then analyzed. To protect the TMD from direct contact with the tip, it is covered with a thin layer of Al2O3, basically scientific-grade sapphire. Even then, the MIM is capable of performing electrical imaging on the MOS2 flakes. Different electrical potentials were applied to the FET, and then the MIM response graphs were obtained from these various voltages. These images show the insulator transitioning to a metal. We also found the average MIM imaginary and real signals in a certain area of the flake. The applied voltage was also converted to a source-drain conductance, which is more useful for our scenario. Here is the graph. The imaginary component of the MIM signal is proportional to the tip sample capacitance, and it increases monotonically until it saturates at the insulating and conducting limits. Let's focus a bit more on the emergence of conductance on the edge parts before the rest of the bulk. Here's an image that shows the conductance appearing on the edge. Finite element analysis is a method of numerically simulating the differential equations associated with the system. Using this method, we can figure out that TMD edges can be treated very similarly to a 1D conductor. For example, the edge channels are responsible for the electron transport when the rest of the bulk is insulating, which is similar to how another condensed matter system works, the quantum Hall effect. To summarize, we were able to use MIM to show a mapping of the local conductance of MOS2 FETs. From conductance maps, we were able to see the phase transition of the insulator-to-metal transition. We were able to see how edge shades contributed to channel conductance, and that is significant until the bulk starts to be conductive as well. In addition, properties such as the electrical inhomogeneity can be visualized using MIM data. This is especially important for finding important electronic transport properties that have applications in fundamental physics and practical engineering applications. Thank you all for watching, and stay tuned for the next video.